We are good to go. So next speaker, the last speaker for today is Markus Kesselring from Berlin, Freie Universität Berlin. I should have known that. And it's collaborative work with Ben Bang, who's also speaking, the first speaker of this session. So yeah, take it away.
Thank you very much for this introduction. And also thank you indeed for organizing this conference twice, once in real space and once in cyberspace now. And also thanks to Barbara and Steve. So first of all, I should start by saying that the title of the talk has changed in between, in between when we submitted the abstract and now, because we have made some progress in the meantime. So now we can add these last 3 words to it. So the title is now Fault-tolerant non-Clifford gates by braiding color code defects in constant time. And as Earl already said, as joint work with Benjamin Brown, who gave the first talk of this session. Okay, let me start with this motivational slide. I'm not only trying to motivate you with some nature, but there's actually a metaphor here. Let me put some labels on here. So right now we're standing on this first spot, which is kind of the 0th generation of fault-tolerant quantum technologies. 0th generation because they're not fault-tolerant at all. That's what the N is for, noisy intermediate scale quantum devices. But we have a relatively clear-cut path, or at least lots of companies kind of agreed on what the straightest path is to a 1st generation fault-tolerant device, which is like some sort of topological error correction codes, most probably the surface codes or some color codes. So somewhere in between here, between the 0th and 1st generation is where the experimentalists live right now. And we as theorists are also moving on from this 1st generation, already think about some next generation codes like these LDPC codes that we have heard about in this talk before us. And okay, in real life, the path probably isn't quite as clear as on this picture. But what I'm trying to do in this talk and in this work that I did with Ben is take you on a small detour, not find the smoothest and fastest path, but take a detour in this like wonderful land of 3D color codes, because I think there's some value and some stuff to be learned that might then make understanding how to get to this point a bit easier. Indeed, like with these LDPC codes, we've heard some of the advantages, but there are also some disadvantages, like we don't know exactly how to do gates with them, but we know how to do gates fairly well with the 3D color code. And that's kind of also what the contribution of this talk will be. Okay, so let me talk by showing you what the 3D color code looks like. Here's a small animation that I hope you can see. Can you see it? Well, this is a lattice, a 3-dimensional lattice that we fly through, and as we fly through, it kind of gets built up. So you can see there are 3 cells, or just cells as I will call them, of 4 different colors, red, green, blue, and yellow, that interlink each other and fill space. Because it's a bit cumbersome to work with GIFs for a whole talk, I made some static images as well. So these were the cells that you have seen in this animation before. And we can actually deform these cells to look like this, so to look more cuboid-like or like shoe boxes by just deforming it. And you can see the mesh of this cell is actually still the same that is on top of this simpler form shell. So for example, the square face here might be the top left square face here. And you can see it is surrounded by 6 hexagons on this ball shape, but also here we have 1 hexagon on the top, 2 in the front, and 1 kind of hidden here behind the corner and the back. If you want to build them yourself, here you have a template that you can print out and fold them up. And now we can start stacking these shoeboxes in layers in a certain way to obtain our 3-dimensional lattice. The cool thing about this lattice is that every second layer looks exactly the same. So in this layer that you see in the very end, you would have a yellow cell hidden behind this blue cell. And on this front layer, so if we jump 2 layers up, we have exactly the same colored cell, a yellow cell in exactly the same spot. Which means if we look at this whole lattice from this direction, so parallel to this edge, we'll kind of see a picture like this. So here all of these solid filled shapes represent one of these cuboid cells. On all of the even, say, layers of this lattice, and the odd layers are only shown by the outlines of the cells here, which is a kind of a convenient way of drawing this 3-dimensional lattice in 2 dimensions. For the talk, though, I'm mostly going to stick to like the actual 3D pictures because they're clearer to see. Okay, so far I've only shown you a picture, but I promised that I would want to talk about an error correction code, namely the 3-dimensional color code. So what do? We do what we always do with these topological codes. Once we have a lattice, we take a bunch of qubits and put them somewhere. In this case, we put them on the vertices. So all of the vertices in our lattice will host one single physical qubit. And then we take some cells, so in our case, 2 and 3 cells, and associate stabilizers with them. So all of our 3-dimensional shapes will be associated with X-type stabilizers, which we call X-cell stabilizers. Here you can see, so we have these weight 24 X checks that check the parity of this weight 24 X Pauli word. And we write them down as S for stabilizer, then the subscript C tells you that it's acting on a cell, and the superscript X tells you in which places it's acting. Okay, and similarly, we introduce C phase stabilizers. Oops. We introduce C phase stabilizers. So these guys, we write them as S sub F for phase, superscript X, superscript Z, and they look like this. So you have weight 6 and weight 4 phase checks on all of the phases that you can see in these lattices. So that's the stabilizer model of the 3-dimensional color code. And now that we know what the stabilizers look like, we can see how to violate them. So to violate these cell X stabilizers, we can apply a bunch of C rotations. For example, if we take 2 Z rotations on neighboring qubits that lie on an edge, or that share an edge which connects to yellow cells, these 2 yellow cells, these 2 yellow X cell stabilizers will be violated. And then we continue the string by doing a bunch of more Z rotations, and then we get point-like excitations at the end of these string-like strings, or one-dimensional strings. And similarly, if we do X rotations, we have to do everything 1 dimension higher. So instead of doing 1-dimensional lines, we now have to do 2-dimensional membranes of X flips. It's kind of hard to see maybe on this picture, but all of these 6 qubits get flipped in the X spaces, which means that the neighboring faces will get violated, and we get this loop-like excitation which lives around it. We can also increase the size of this loop-like excitation by flipping a bunch more faces of the same color, this yellow and blue color, for example. These are the 2 types of excitations that we live with, the point-like excitations and the loop-like excitations. Okay, and now we're almost there, so we're almost ready to encode some logical qubits into this thing. The next thing we need is boundaries. So to get a boundary, or one type of boundary, the colored boundaries, you can just really easily get them by cutting off the lattice and reducing the size of, so throwing away all of the qubits that live on the right of this wall that we built here, and changing some of the stabilizers that live here. For example, these red cells now only are half the size, so they only act on 12 qubits here, and the green guys also get a bit reduced in size. And as you can see, if we look face on this wall, we don't see any yellow cells, so that's why we call this a yellow puncture. Now we can take our 3D blob of 3-dimensional color code, some volume in space, and cut out 2 ball-shaped regions, and do this in a clever way so that we get the yellow boundaries all around them. Then we have 2 punctures which are able to encode 1 logical qubit. And the logical operators associated with this qubit is just a string connecting the 2 punctures along yellow edges, as we have seen before, which could be our logical Z operator, and the membrane which engulfs one of these punctures completely, which could be our X logical operator. Okay, so that's the regular 3-dimensional color code, as it has been discussed a few times already. One thing lots of people don't really know about is that the different way of describing this 3-dimensional color code is through the use of the XS stabilizer formalism. So let me go through this rather mathy slide. So up here are just the regular Pauli matrices that I'm sure all of you have seen. And next we can take the square root of this Z, Pauli Z matrix, and we get this 1 and I on the diagonal. I have plus and minus I here for some technical reasons that we'll need later, but don't worry about it too much. So this is just our phase gate, and if we take the square root of this guy again, we get our famous T gate, which is a non-Clifford gate. And now I actually want to get at is this W operator that this W basis that I'm introducing, which is a Clifford basis that we get by conjugating the X Pauli X with this T guy from the left and right. And if we do the math, we see it's X plus minus Y over the square root of 2, or equivalently can write it as some phase times X times S, which is where the name XS stabilizers comes from. Okay, so again, here is the definition of this XS stabilizer. And now we can I try to and want to convince you on this slide that if we take this W basis and act it on a cell, then that whole thing is also a stabilizer. So there's indeed, this notation is valid. Then we have stabilizers which act on cells in the W basis, and they actually stabilize our three-dimensional color code. So that's what this operator would look like. Another way of thinking about this cell stabilizer is by just taking an X cell stabilizer and conjugating it with a transversal T gate. So if you are already convinced that the three-dimensional color code has a transversal T gate, you're probably convinced that this is true, what I'm saying here. Okay, now the way I try to convince you is by looking at the commutator of these W cells with surrounding stabilizers, for example, with a surrounding set check on a face. And here, if you do the math, we see the group commutator of these guys is actually just +1. You can do this by realizing that S and C are both diagonal in the computational basis. And we already know that the X cell and the Z face commute. So that's an easy thing to check. A bit more involved is this relationship. So if you have two neighboring cells, C and C prime, and they overlap on one face, then the commutator between the two W stabilizers acting on these cells is exactly the the phase check in the Z basis of the face in between the two of them. Okay, and now with this knowledge, and knowing what this stabilizer looks like, what this commutator looks like, we can do some math and in the end see that if we act this W cell on our color code state, we actually find that we're in a +1 eigenstate of this color code state again. Here's the math if you want to go through it yourselves. So that means these W cells that I showed here are actually also valid stabilizers for a three-dimensional color code. Okay, and that implies, as I said, that we have a transversal T gate. But here I want to go a different direction with the knowledge of this transversal gate. First, let me quickly, for the people that are familiar with the two-dimensional color code, you've heard a bit about it yesterday, for example. There we know that all the single qubit Clifford gates are transversal, in particular also this S gate, this phase gate. And what happens if we apply this to a subregion of, so let's say this is our two-dimensional color code inside this gray blob. And in this two-dimensional subregion, we apply this transversal S gate. Now let me zoom into the bottom region here. We can see that we get a domain wall running through here, and the stabilizers which are cut by this line are now acting in mixed bases, so X on the bottom and Y on the top. And all the stabilizers up here are actually still, you might be tempted to say they were changed as well, but because we're still in the color code state, we can actually also just measure the original stabilizers in this region, and we're still in the same state. And something very, very similar is happening in 3D. Everything is one dimension higher as always. So here now you have to imagine that this gray region is actually a three-dimensional volume of three-dimensional color code. The subregion that we pick now is a ball-shaped subregion, and instead of applying a transversal S gate, we apply a transversal T gate. And inside this region, all of our X cell stabilizers are now changed to W cell stabilizers. But as I've tried to convince you before, that's still just stabilizers of our three-dimensional color code. So in here, we're still in the same code as out here in any 3D color code. But along this domain wall in between these two regions, something special happens. So here's the 3D picture again, and you can see this orange domain wall running through it. And stabilizers that are cut by this domain wall will now be changed a bit. So for example, this green guy, you can see I've highlighted all of the qubits to the right of this, which are the ones that lie inside this region. They're now measured in the W basis, where the qubits on this left are measured in the X basis. So here we have a mixed stabilizer that acts in the X basis on parts of the qubits and the W basis on other qubits. That's how we can introduce this domain wall. Okay, now what happens if we cross this domain wall? So before I showed you how we can create these loop-like excitations by applying membranes of X flips. Now we can enlarge these membranes by just flipping more and more qubits in the X basis, until eventually we cross this domain wall and get out the other side. And now to still anti-commute with all of the stabilizers in the right way that we want them, or commute with the ones that we want to, we now actually need to do all of these flips on this side in the W basis. So that means excitations that wander through this domain, through this magic domain wall will also be changed from acting in the X basis to acting in the W basis. And we can take use of this because we know that there is a relation between how to create excitations and our logical operators, as I've seen before. to now actually apply non-Clifford gates to qubits that are encoded in a certain way. So here, what is drawn on the left, that's a hollow sphere with a pattern of colored boundary around it that looks like this. So you have red, green, blue, and yellow boundary patches that meet in a certain way so that each pair of colors share an edge, and you have four of these triple points. And this encodes one logical qubit in our color code. And if we start, for example, with a qubit encoded in the plus state and then move it through this domain wall, we end up with a qubit in a magic state on the right of it. That's why we call this domain wall the magic domain wall, because it applies magic gates to certain encodings of qubits. Okay, so I told you all we need to do to apply a magic gate is just take this puncture encoded qubit and move it through the domain wall. How do we actually move these punctures in a three-dimensional color code? The way of doing it is through the use of code deformation, which Ben mentioned in his talk as well. So this picture kind of reminds me of how in Star Trek, whenever the warp drive gets activated, how the Enterprise flies away by just stretching out and then disappearing into the distance. Something very similar is here actually happening as well. So we can take our puncture and just increase the size of it by removing all of the qubits in this area, and now get a really large puncture. And we can actually do this in just one single time step by just changing the measurements of the stabilizers around it and measuring in clever bases here in the center. And now we have this extended puncture. It also works in 2D and just constant time. The tricky part now is to collapse this whole puncture down to only have it in the right, because we have all of this, what previously was empty space. We now have to fill it up with a valid three-dimensional color code state again. And to do this, we need to measure all of the stabilizers in here. But the good thing about the three-dimensional color code is that we can measure all of these stabilizers in just a constant number of times. So that means this reinitialization of the three-dimensional color code that we have to do to get from this middle step to this bottom step can be done in a constant number of steps, or a constant number of times of time. Okay, and how does this work? This works through what is called single-shot decoding. We make use of the fact that the three-dimensional color code can be, there's a related code, the gauge color code, the three-dimensional gauge color code. And instead of measuring all of the cell stabilizers, we just measure phases and multiply the outcomes together, similar to what Nico talked about in his talk just before mine. So for example, if you want to infer the value of the X parity of all of the 24 qubits on this volume up here, we can instead go ahead and measure all of the square phases and the X parity thereof and multiply them together, and the outcome will be the same. And there are actually two other ways of measuring hexagonal phases in this lattice to get the same outcome. So this is a bit involved because all of these operators that we measure here don't commute with the Z phase operators that we measure in other time steps. But there are tricks around this. I mean, it just ends up working out because the stabilizers still commute. Okay, I probably don't have too much time to go into this, but the good thing about this trick is that now we can get away with measuring all of these gauge terms just once and do a decoding with get a finite threshold for a three-dimensional color code, even in the presence of measurement noise. So we measure a bunch of these phase operators, and even if they're wrong, we can pick up on like some gauge excitations and match them up to get our correction in the end. If you want to know more about this, this talk is probably not the time to learn because I'm pressed on time, but just Google gauge color code and you'll find good references. Okay. So now, as I said, we want to make this code deformation of our puncture encoded qubit on the left of the domain wall and move it through the right by extending first the puncture and then collapsing it again. And in this collapse, and when we collapse it, we need to measure a bunch of phase operators now instead of cell operators to do this gauge error correction. And here on the left of the domain wall, everything is fine and dandy because we can just measure all of these cells in the X bases. The ones that are cut in half or cut by this domain wall, we now have to measure these phases in mixed bases, so half X and half W, depending on which side of the domain wall the qubit lies. And then the ones on the right, you might be tempted to think, okay, let's just keep measuring W, because otherwise we might run into issues of like the way these guys overlap. But actually, we also run into issues if we keep measuring this in W, because we could also go around the other way, around this domain wall, which we eventually have to do with this qubit to get it back to its initial position. So there's actually, while we do measure the X and W faces here, in the same time step we measure all of the X faces out here. So this guy here is a bit problematic because it will either it has a W face as its neighbor and an X face as its neighbor. And if we look at the commutation rules that I've shown you before, if we take two of these phase operators, one acting in the W basis and one acting in the X basis, on neighboring faces F and F prime, which are only overlapping on one qubit, for example, their commutator is proportional to the Z operator on that qubit here in the middle. So that means the fact or the question, do they commute or not, depends on a single qubit in the code, or sometimes also pairs of qubits, depending on which phases you ask about, which is not ideal and a bit problematic, which is also why we, for a long time, weren't sure if you can actually do this whole procedure also still in single time. Now we found a solution to it, which is through the use of science fiction again, or actually just regular space travel, by the use of making use of airlocks. So the picture from NASA. Okay, so let me explain how the airlock looks like in our case. So we start with our encoded qubit here, as we have seen it before, and the domain wall here in the center of the code. But now we take this domain wall and embed it inside a sphere of three-dimensional color code, which is separated from the rest of the color code by this hollow sphere of vacuum, or just empty air, fresh air in between the two, these two parts of the color code. And now to get the encoded qubit from out here inside here, we open our airlock on the left and then push the qubit in. And now we can close it up again. And now we do the step that I've talked about before, where we just do code deformation to go through the domain wall. And now to get it out the other side, we open the airlock again, push it out and close the airlock. So this is our procedure without the steps where the airlock is open, shown in here. Now I can explain a bit in what basis you need to measure. So outside of this whole contraption, we always measure all of the faces in the X basis, as we always would. And here on the left side, before we start the procedure, we just measure all of the faces in the X basis, and on the right we measure them in the W basis, for example. This is still true when we go with the qubit inside of this in the sphere and through the domain wall. But now in this time step, or from here to here, we can at one time step just change the basis in which we measure the stuff. So now we measure W on the left and X on the right, which is a valid thing to do because all of these guys will infer the value of actual stabilizers of the W cell stabilizers on the left. And here we also always had these X stabilizers on the right, whose value we now infer. But now if you open the airlock, we don't run into any trouble of having neighboring W and X faces anymore. So we can take the qubit out safely and apply a transversal T-gate to it. Okay, well, this went a lot quicker than I imagined. So I'm already kind of at the conclusions of my talk, which is good, so we have more time for questions. Okay, so let me quickly go back to this picture that I've shown you in the beginning. So we took this detour to the three-dimensional color code. And I kind of explained how we can do gates with it in just constant time by braiding them, which might be very valuable to know for LDPC codes, because as I mentioned, LDPC codes and doing fault-tolerant gates is still a fairly open question. There's been some work that you can read up here by Anirudh Krishna and David Poulin that I would like to point out, where they make a construction of these hyperproduct codes, which are related to surface codes in a certain way, so that you can take punctures from these surface codes and kind of generalize them to these LDPC codes. And because we know how to braid punctures in the surface code to get certain gates, we now know how to do this with LDPC codes as well. And now we also have a way of doing non-Clifford gates through braiding alone with the presented procedure that we've seen before. So maybe that could give some insight in how to do non-Clifford gates in LDPC codes through braiding with similar ideas. Okay, I'll just kind of wrap up the talk by giving a summary. So I've shown you the three-dimensional color code and maybe a new way of looking at it in just this two-dimensional pictures that you haven't seen. And we have seen that we can take these punctures and move them around by using this warp drive trick from Star Trek to get the right. And with this trick, we can move them through these punctures through our domain wall to apply non-Clifford gates to them, but to still have this all work in this in a single in a constant time. So in the to be able to use single shot decoding of the three-dimensional color code, we need to make use of this Airlock. And as an outlook, might use this technology or these ideas later on to do some wormhole braiding tricks as presented by Anirudh Krishna and David Poulain. Well, that is it from my part. Thanks for well, I assumed you all were quiet and listening to my talks. Thanks a lot for that. Questions? Are you still here?
I'll ask a question. You know, some years ago, Rausendorf showed how to do Clifford gates by braiding punctures. And only later was it shown that you could also do those Clifford gates using lattice surgery with patches.
Mm-hmm.
What you've shown today is a way to do non-Clifford T-gates by braiding punctures in a 3D color code.
Yes.
Is there a straightforward generalization of how you might do this with lattice surgery between, quote, patches of 3D color codes? Maybe they're like tetrahedra or something like that?
Yeah, I think if you look at the recent work from Hector Bombin, he kind of talks about this when he takes these twisters of three-dimensional color code patches, which are tetrahedral shaped. And there is a certain way of reading these results where you do lattice surgery between these patches, and you just apply transversal T-gates between them and then use lattice surgery to teleport the information through your stacks.
But is there a way to understand it in terms of this transition, you know, going through the domain walls with W, you know, this X to W kind of translation that you're talking about with the punctures here, or not so obviously?
I mean, kind of. So there is a picture that I don't have here. So these domain walls and the transversal gates, they are kind of related. If you think about the 3+1 dimensional space-time volume of these codes, then applying a transversal T-gate is kind of applying one of these domain walls in a vertical manner, so perpendicular to the time direction. And what we try to do here is just rotate it out of space and have it just only fully living inside the free space and not the time direction. So lattice surgery is kind of using, or at least the way Hector Bombin does it, I try to explain, is the using these domain walls, but in a time direction.
Okay, thanks.
Or I hope that answered the question, otherwise you can still chat on Slack.
Hi, Markus. Sorry, I missed a couple of minutes there. The most terrifying thing happened. My screen just went black.
Oh, no.
It wouldn't power up again for a while. Completely
Right.
suddenly, when you were talking about airlocks.
Yes.
So I hope the rest of the talk went okay.
It was quicker than what I planned, but yeah, it went okay.
So I have a question, which was about airlocks, because I missed that bit. So can you just tell me, I think actually I missed what the motivation for airlocks was. Like, why do you need an airlock?
Okay, so yeah, sorry if that wasn't clear. So the problem if we don't do this Airlock trick is if we want to do our code deformation still in constant time, we need to make use of the single shot decoding properties of the three-dimensional color code, which means instead of measuring full 3 cells of stabilizers, we only measure 2 faces. And this just gets very complicated because now these faces overlap in non-nice ways, so that the commutators between neighboring faces, especially if they act in different bases, not if they act in the same bases, now depends on single qubit and 2 qubit states.
A decoding problem, essentially, at the boundary. Sorry? It's a decoding problem, essentially, but
yeah, exactly.
Okay.
We don't know how to do the single shot encoding if we don't do this. If you were able to measure all of the 3 faces and still have the single shot property, 3 cells and still have the single shot property, then all of these airlocks wouldn't be necessary.
And I don't know if you've already had this answered or asked, but Giulio Magdalena has asked what happens to the individual puncture when moved through the magic domain wall, i.e. not the whole qubit, but parts of it. Does that make sense?
So
the question is, what happens to the puncture when it's moved through the magic domain wall?
Instead of the logical qubit that is encoded in it, so the puncture itself doesn't really change. So here, the puncture is just given by a bunch of stabilizers that are removed on the inside and a bunch of stabilizers that are changed on the surface. And they still will look exactly the same afterwards if you go through the whole domain wall at the end of this process.
Mm-hmm.
But if we keep track of the logical operators, you can see the way they change. We actually apply a logical T gate to them. I hope that answers the question.
I guess there's a little uncertainty there. So maybe if we can unmute Julio, and if Julio wants to ask the question, then. Does anyone else have a question? Do we have Julio live to comment on whether their question's been answered or not? No? Okay, well with that, I guess we'll thank Markus again and give him a virtual round of applause on the Slack channel.